All right, so welcome to MathStat 341 probability. And what we're going to do today is we are going to talk about the theory of the exponential function. Have we proven the basic properties of the exponential function in this class? You did? Okay, I didn't think we had. We'll then talk about Stirling's formula, and we'll talk about how to get results towards Stirling's formula. So Stirling's formula is estimating the size of n factorial, one of the most important objects you will see in probability and statistics. And you need to get a sense of how quickly is this growing. We will then talk about Poisson random variables, which is going to be a wonderful class of random variables. It's going to be another example of a stable distribution. So what is a stable distribution?
Yeah, subtract two to create another version of that.
Good. So when you add or subtract, you still have something of the same form. The parameter might change. You know, the normal of a sum is a normal. I'm sorry, the sum of two normals is normal, but it doesn't have the same parameter. The variance will grow. And then the last is we will see how the central limit theorem actually implies Stirling's formula for approximating n factorial. And what I love about this is it shows you that just because you prove a result and you have in mind one application, doesn't mean you can't use it for something else later. And so when we think of the central limit theorem, we think about using this to try to estimate sums of random variables to try to approximate probabilities. We can use this to prove Stirling's formula. We have to be a little bit careful, and I will make a little comment about that. So just so that we're all on the same page, and I will repeat this slide later, this should be eventually ingrained into your memory. The normal distribution with mean mu variance sigma squared is the following. And then the central limit theorem says if we have a bunch of independent, identically distributed random variables who have mean, mu, variance, sigma, both of these are finite. If we look at the sum and then divide by n, so we get the average value, that converges to being normally distributed. And this is not like the Ohio State University. There's many different normal distributions we can get depending on how we want to normalize. Do I want to take the average? Do I want to divide by n? Or do I want to just look at the direct sum? Maybe I'm tossing a fair coin and I want to know how many heads have I gotten. Well, I don't really want to know the average number of heads. I want to know how many heads have I gotten. Frequently, we look at the standardization. So what we do is we take the average value and we subtract the mean, and then we divide by the standard deviation, sigma over square root of n. The advantage of that is we now have a random variable that has mean 0 and variance 1. So that if we need to have tables of probabilities, we only need one table, the table for the standard normal. I can convert any normal variable by just doing a simple rescale to a standard normal. This is very similar to logarithms. You really only need to know logarithms in one base, and then you can use the change of base formula to move from one base to another. In the days when people used to compute these things by hand, it was really valuable to only have to have one. Old probability textbooks would actually have tables in the back about probabilities of various distributions, especially the normal distribution. They would have tables often of factorials. In the 21st century, this is no longer really as needed, but it's just worth being aware of which do you want to study. This is to try to compare apples to apples. Is we always standardize and we make something have mean 0, variance 1. When we prove the central limit theorem, it's amazing that it doesn't seem to depend that much on the random variables, that you get this incredible universal result. And this is the big result of the class. Why do you always get the same distribution back? Why does the shape of the distribution not matter? It turns out when you do the proof, the only thing that really matters to contribute to the main term is the mean and the standard deviation. The higher moments only surface in the proof, and we'll get to this, in terms of the rate of convergence. Well, if I can always adjust my probability distribution to have mean 0, and I can always adjust it to have standard deviation 1, that's where the universality is coming from. The shape of the distribution will affect how quickly it converges to being normally distributed. Anybody have a thought about which choice for density of the x's will converge to a normal fastest? Normal, right? Make it real easy. Start with a normal, right? It's going to be normal immediately. So then an interesting question might be, modulo some reasonable conditions, what is the worst distribution I could take? How many of you have taken a statistics class where you hear the rule of 30? You have roughly 30 observations. You can say, yeah, it's normalish. Hopefully they say normalish and not normal. Where does that 30 come from? Well, for a lot of distributions, if you have 30 data points and it's not too pathological, it's pretty good. All right, so this is the exponential function, 1 plus x squared over 2 factorial, and so on and so on and so on. You can begin to see why I might want to talk about Stirling's formula and estimating factorials today, given that we're starting with the exponential, and this is going to be the key building block when we get to Poisson random variables. So what is e to the x times e to the y? E to the x times y? It's not x times y, plus y, laws of exponents. What is cosecant of x? 1 over sine of x. And I may have ranted about this earlier in the semester about how this offends me. Right? Yes, I will continue. It's just wrong. Right? You want to put sine with secant and cosine with cosecant. Well, maybe we're just trying to split and make sure each one gets a covariance. You have to be careful. Math can't have bad notation. What does e to the x mean? E to the x technically means an infinite sum. What does e to the y mean? It technically means an infinite sum. What does e to the x plus y mean? It technically means an infinite sum. Now, when you see e raised to the x, you think the number e 2.718 raised to the x power. But technically, it's an infinite sum. If this result were false, if e to the x, e to the y was not e to the x plus y, then we would be guilty of horrible notation. Well, unfortunately, that crime has been committed in the past. Almost surely it will be committed again. And so we have to be careful. Is this actually good notation? Do we have e to the x times e to the y is e to the x plus y? So have we discussed why this is true in this class? Okay, so this follows from the binomial theorem. So e to the x, e to the y is going to be the sum, n goes from 0 to infinity, the sum m goes from 0 to infinity, x to the n over n factorial, y to the m over m factorial. I am not going to worry about justifying any of the convergence. What class will you do that in? Real analysis. But basically, we have the factorials. Everything converges so well that it's fine. You should have taken multivariable calculus, and you should have seen Fubini's theorem in multivariable calculus, which talks about when can you switch the order of integrations. It's often not proven in 150, 151, but if the absolute value has a finite integral, then you can switch orders. It's the same with sums. If you put in absolute values and the absolute value of the sums converges, then you're fine. And we have so much decay from the factorials in the denominator that we're going to be okay. So when we expand this out, we're going to have a bunch of terms. We could have n and m equals 0, and we'll just have the term 1. Or we could just have x, we could just have y, we could have x squared, xy, y squared. We split things up based on the sum of the powers. So split by sum of the powers. And so I claim this is the same as, say, the sum k goes from 0 to infinity, the sum L goes from 0 to k, x to the L, y to the k minus L, over L factorial, k minus L factorial. So what I'm saying is, look, whenever you have x's and y's together, take and group together the ones where the power n plus m is equal to k. So basically, we want k to be n plus m. So really, what letter could I use for L if I wanted to? I could just keep L as equal to n. I'm just grouping things together. So now it's time for pattern recognition. We have an L factorial and a k minus L factorial. Does this remind you of anything? Yeah, what do you need to make this a binomial coefficient? So let's just put a k factorial on top. Can we do that? What if we really want? Yeah, or just divide by it as well. As long as we multiply by 1, it's legal. And so now we notice that k factorial over L factorial, k minus L factorial, that's just k choose L. So this is going to just be the sum, k goes from 0 to infinity, I can pull out the k factorial from the denominator. I have the sum, L goes from 0 to k, and I will have k choose L, x to the L, y to the k minus L. But what does that equal to? So what is the sum k choose L, x to the L, y to the k minus L? Yeah, this is just x plus y to the k over k factorial, and this is the binomial theorem. And by definition, that is just e to the x plus y. So this is a proof that this is actually good notation. Notice here, if I try to ask, what does it mean to raise a number to the square root of 2th power? I have no idea. I know how to raise something to an integer power. I know how to square something. If you want me to take the square root, so if I want the square root of x, that's the same as searching for a number y such that y times y equals x. Oh, okay, I know how to do a search like that. I can just slowly keep increasing y until it hits. But to raise something to the root 2th power, that's hard. If you look at the definition of e to the x, you're just raising things to integer power. So no matter what x you put in, the series expansion for e to the x makes sense. And that's what's so wonderful about this. So we needed a little bit of theory here to just justify what's going on. Okay, so we talked a little bit about the gamma function before. So the gamma function is a generalization of the factorial function. So gamma of n plus 1 is n factorial. We talked about why would we write it as x to the s minus 1, since this is the day that Audie started with the cosecant, why would you choose to define it with an s minus 1? Because it's often convenient to have dx over x. And because of that, that's why we write it as an x to the s minus 1. So Stirling's formula says that when n is really large, n factorial is approximately n to the n e to the minus n squared of 2 pi n. And that means if you take the ratio of these and let n go to infinity, that goes to 1. Or if you wanted to be a little bit more careful, you could actually write out a series expansion for n factorial. If I tell you all of a sudden that you owe Williams College $100,000, how do you feel? Okay, if anybody doesn't mind, please see me after class. Okay. All right, so everybody agrees that if you find out all of a sudden that you have an extra $100,000 in late charges, you're not happy. What if I tell you there was also an error in the other way, and we just realized Williams owes you $512 million? That would be cool. Would you be okay with owing Williams $100,000 if Williams told you we owe you $512 million? Yes. So, and just to make sure no one owes $100,000, and to my knowledge, no one is about to get $512 million. Okay. Sorry if anybody was hopeful. The point of this is that when I'm talking about sizes of terms, it's all relative. $100,000 might seem large at first, but then when you compare it to 512 million, it's nothing. So when you look at this, if n is huge, if n is like, even 100, 100 to the 100, oh my God, that's huge. Or actually 100 over e to the 100, huge. Now, this term is smaller, but it's still going to be a huge term because it's multiplied by this incredibly large number. How much smaller? Well, it's about 1 over 1,200 times. So it is, smaller, but it can still be large on an absolute scale. So when we have expansions like this, we just say, this is the main term, the next piece is significantly smaller, but it can still be quite a large number. When you see something like this product, what is your first instinct whenever you see a product? After taking a class with me. To take the log. And so if I take the log, then this becomes a nice piece when I take the log, and then I have the log of 1 plus something small, and you can Taylor expand that. And it's a really good way to analyze this. We have a lot of math devoted to understanding sums, and so if we take logarithms, we can convert from products to sums, and then we can use all of those tools from calculus. And we'll do that very, very shortly. So the first is, this is your chance to be a smartass. I want crude upper and lower bounds for n factorial. I will accept anything correct. Can somebody give me either an upper or a lower bound? 0. Yep. Can you do better than 0? 1. Can you do better than 1? Without too much work. N. Okay. So those are all acceptable lower bounds. What about an upper bound? N to the n. So these are really good, quick, fast bounds. And if somebody had really wanted to be a smart, they could have said -5 or something like that. And then that, yes. At least once you hit 1 and n, these are reasonable bounds. For the bound of n, we're just saying, well, look, let's look at all the terms and take the largest term and drop everything else. That's got to be a lower bound. And for the n to the n, we just say, let's replace every term with the largest term. The problem here is these bounds are so well separated that it's not even close to the truth. Now we have a beautiful theorem that if you look at the sum of the integers up to n, this is n plus 1 over 2. Wonderful, wonderful result. There's a lot of ways to prove this, but let's just try to get a bound. So let's call this S of n. Can somebody give me an upper bound for S of n? N squared, right? There's n terms, and each term is at most n. Can somebody give me a lower bound? 1, okay, give me a little bit better lower bound than 1. N. So this is actually much better than, than the factorial in terms of how close they are, but they're not the same order of magnitude. So a lot of times I really just care, how is it growing with n? I don't necessarily care about, is it growing 3 times this rate or whatever, I just care, what is the n dependence? And so we can get a better lower bound. Lower bound, n halves times n halves, which is n squared over 4. Have n halves plus n halves plus 1 plus dot 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 plus n over 2 terms, each is n over 2. So if I just do a simple calculation like that, I now have it's at least 1/4 n squared, and it's at most n squared. Okay, so now I have the order of magnitude. So I have my upper and my lower bounds are at least of the similar scale. I'm not going to bother, writing this down slowly. It's all on the slides. You can just do some quick tests to see if Stirling's formula is correct or at least reasonable. Let's look at n plus 1 factorial divided by n factorial. We know that's just n plus 1. So let's just put in what Stirling says for n plus 1 factorial divided by n factorial. And if we do a little bit of the algebra, we get it's n plus 1 times 1 plus 1 over n to the n, e to the minus 1 square root of 1 plus 1 over n. Well, as n goes to infinity, 1 plus 1 over n to the n is the other way of defining the function e. And this is just e to the first power. That's going to cancel with the e over here. Oh, okay, this is giving me maybe a little bit of an insight as to why e is popping up in Stirling's formula. And again, whenever you have interesting things going on, it's always worth asking, where is this coming from? There's been some hints about this, but we've talked a little bit about e. We also have this number square root of 2 pi. Where have you seen the square root of 2 pi before? The normal, the normalization constant of the standard normal. We've talked about how the gamma function is related to the moments of the standard normal. Maybe it's not so surprising then that this is showing up in Stirling's formula. But until you start doing these calculations, it's like, how is Stirling's formula involving both, pi and e? Yeah, that's a little strange. All right, how many of you remember the integral test from calculus? I'm debating if I should mute this so I can swear. This is it's similar to Riemann sums. And so if you have a function that is either non-decreasing or non-increasing, you can approximate the sum by converting it to an integral. So what I'm doing here is, let's take the log of n factorial. The log of n factorial will be the log of 1 plus the log of 2, all the way up to the log of n. And now if I look at that, what function, can you give me a continuous function that equals the log of 1 at 1, the log of 2 at 2, the log of 3 at 3. Any thoughts on what might be a good continuous function? Yeah, log x, log t. So f of t is log of t. So there's my continuous function. This is similar to when you're doing some of the tests in calculus and you want to convert from the series. You just replace the index n with a letter x or t, whatever you want to use. So if I look at the function log of t and I plot it, I have to be a little bit careful. If I look at the log of 1 plus the log of 2 all the way up to plus the log of n, well, what is it? If I multiply each one of these by 1, it's going to give me the area of a box with height log k and width 1. So the first box over here is just going to be, the log of 1. Well, I guess no, sorry, this one is going to be the log of 1. This would be the log of 2. This would be the log of 3. This would be the log of 4. And what we're doing is we start at the left and we take that value for the whole thing. Well, the function is going to be above that. So the area under the function is going to be greater than the sum of these rectangles. Okay. And then the other way, of course, is going in the other direction, where instead of having it go to the right, I have it go to the left. If I do it that way, then it's going to be above the function. And so you can basically say with a little bit of algebra, the sum of the log of k is sandwiched between these integrals. And they really only differ by the last term. One of them goes from 1 to n, one of them goes from 2 to n plus 1. So the error is really going to be bounded by just the last term, which is going to be much smaller. The last term is of size log n. And that's much, much smaller than what we expect the log of n factorial to be. So this is the power of the integral test, is we can often get really good estimates without too much trouble. And so when we apply this, we need a function whose derivative is log t. So we claim that t log t minus t has derivative log of t. And that's what we need to make things work so that we can do the integration. This is found by the method of divine inspiration. I want to find a function whose derivative is log of t. If I look at t times log t, well, the derivative of t is 1, so I get log t, which is great. But unfortunately, there's the other half of the product rule. I would then get t times the derivative of log t, t times 1 over t. Ah, crap, I get log of t plus 1. Well, I just need to subtract a function whose derivative is 1. It's just t. So when I plug this in, I can now get your bounds. And just after a little bit of work, I get here's my lower bound for n factorial. N to the n, e to the minus n times e. That's not so bad. If you go back a page, the upper bound would just differ by an extra factor of n. So we differ by a factor of n, which seems a little bit large, but when you consider how large n to the n, e to the minus n is, differing by n is not huge. The other thing is, as a nice remark, we have the factors 1 and n. What's the average of 1 and n? It's n plus 1 over 2 if you use the arithmetic mean. Does anybody know another way to average numbers? You could take the square root. And in fact, that's the geometric mean. So the geometric mean of two numbers is their square root. And for us, that's going to be the square root of n, which is exactly what Stirling is supposed to be. It's supposed to be of size n to the n, e to the minus n, square root of n. And since we're doing logarithms and we're really coming from a product, the geometric mean is actually a more reasonable thing to look at. If you got a 0, well, let's say you got a 1 on your first test and 100 on your second, what's your average approximately? 50. And if we take the geometric mean of 1 and 100, so what might you think relationship-wise do you have between the arithmetic mean and the geometric mean? Which do you think is larger? Yeah, I mean, this is only one data point, but you can prove the arithmetic mean is larger. For certain problems, though, the geometric mean is a better one to look at. All right. I'm not going to talk about the Euler-Maclaurin formula. I'm just going to post this here on the notes in case anybody is interested. There's a whole theory about how to approximate sums by converting them to integrals. And not surprisingly, the smoother your function is, the more derivatives it has, the better answer you can get. It's just getting this on your radar. right, now it is time to get to the Poisson distribution. So this is another one of the classic distributions. So lambda greater than 0 is a parameter. And then we take on non-negative integers, 0, 1, 2, 3. And the probability we take on the value n is lambda to the n, e to the minus lambda over n factorial. And it turns out that the mean and the variance are both lambda. So we will compute this. Before we compute this, what's the first thing we have to do? So I'm telling you that this is a probability distribution. We should check. So is it non-negative? Yeah. Clearly non-negative. Does it sum to 1? Right? That's the problem, is does it sum to 1? All right, well, let's look. So we have the sum, n goes from 0 to infinity of lambda to the n, e to the minus lambda over n factorial. I can pull out the e to the minus lambda, and I have a sum from 0 to infinity of lambda to the n over n factorial. Oh, but what is lambda to the n over n factorial? It's just, I couldn't hear you with the math. Yeah, just e to the lambda. So we just get e to the minus lambda times e to the lambda, which is just 1. And so that does finish the proof that it is a probability distribution. I'm going to save the following. We know the sum n goes from 0 to infinity of lambda to the n, e to the minus lambda over n factorial equals 1. That implies e to the lambda equals the sum n goes from 0 to infinity of lambda to the n over n factorial. Why do you think I might be saving this? What might this be useful to find? Yeah, to find other moments, differentiating identities. I need an identity to start the process. I could keep it as this expression equals 1, but then when I differentiate, I'd have to use the product rule. And I'd rather not use the product rule. So I'd rather just move it over to the other side, differentiate, and then move it back so that it becomes my probability distribution. All right, so this is a Poisson random variable. So the first thing we want to do is we want to prove that the mean is equal to lambda. Okay. There's a couple of ways to prove this. We could use the fact that, e to the lambda is equal to the sum n goes from 0 to infinity of lambda to the n over n factorial. Let's apply lambda d by d lambda. When we take the derivative of e to the lambda, we just get back e to the lambda. So we just get lambda e to the lambda is the sum n goes from 0 to infinity of lambda d by d lambda of lambda to the n over n factorial. And so again, I'm using the fact that the derivative of a sum is the sum of the derivatives. You have to justify this. But when we take the derivative, we now get the sum n goes from 0 to infinity of n lambda to the n over n factorial. And so if we just bring the e to the lambda back over, we get the sum n goes from 0 to infinity of n lambda to the n e to the minus lambda over n factorial. And that's just the expected value of x. And if I wanted to calculate the variance or the second moments, I would just apply it again. So it works pretty nicely. There's another way to do this calculation. And we could go back to say, well, the expected value of x is the sum n goes from 0 to infinity of n times the probability x equals n. So it's sometimes nice to see more than one way to do something. So it's n times lambda to the n e to the minus lambda over n factorial. Do I have to start the sum at 0, or can I move the sum up a little? When n equals 0, I just get 0, right? So I might as well start the sum at 1. So this is the same as the sum, n goes from 1 to infinity of n over n factorial lambda to the n e to the minus lambda. But what's n divided by n factorial? 1 over n minus 1 factorial. So this is the same as the sum, n goes from 1 to infinity of lambda times lambda to the n minus 1. I'm having a lot of fun today, over n minus 1 factorial. I'm just writing lambda to the n is lambda to the n minus 1 times lambda. Well, I can pull the extra lambda outside, and then this is just the sum. M goes from 0 to infinity, lambda to the m e to the minus lambda over m factorial, where m is just equal to n minus 1. So if n goes from 1 to infinity, m goes from 0 to infinity. But this is a probability distribution, and we're summing all the probabilities. That's just equal to 1. So it just equals lambda. So again, for this distribution, you actually don't need the whole theory of differentiating identities. You can actually just do the algebra nicely. As a nice exercise, if you tried to do the second moment n squared, that would be very hard to do. Rather than doing the second moment of n squared, you should actually calculate n times n minus 1. Because n times n minus 1 will go very nicely with the n factorial. And then that will give you not the second moment, but the second moment minus the first moment. And once you know the second moment minus the first moment, since you already know the first moment, you can then get the second moment. So again, as you go further in the subject, it sometimes becomes a bit of a challenge to figure out what is the best way to do the algebra. And if I can calculate something easily, I would much rather calculate that than do something that is more painful. All right. It is now time to prove the result that I promised, that if you have a bunch of independent Poisson random variables with parameters lambda 1 through lambda n, then the sum is a Poisson random variable with parameter lambda 1 through lambda. As we've done numerous times, if I have x1 plus x2 plus x3 plus dot dot dot, it's a proof by groups. It's a proof by grouping. I first group x1 and x2, and then building on that success, I would then group that with x3, and so on and so on and so on. So we've done this argument numerous times. If you can show that the sum of any two Poisson is Poisson, where you add the parameters, you just keep doing it again and again and again. x1 plus x2 gives you a Poisson with parameter lambda 1 plus lambda 2. You then add x3, you get lambda 1 plus lambda 2 plus lambda 3. And so you just march down by grouping, you march down by induction. So we just have to do one special case. All right. So let's say we have x1 is Poisson with parameter lambda 1, x2 is Poisson with parameter lambda 2. Let's let x be x1 plus x2. Then the probability that x equals n is going to just be the sum. M goes from 0 to n. The probability x1 equals n, so equals m, times the probability x2 equals n minus n. Because if I have a sum, if the sum is going to equal n, then the first one has to be m, and the second one has to be n minus m. I can't have my first summand be larger than n, because the probability of a negative number is 0. What method am I using here? This is the, you have a word for this. We've only done it for integrals. This is the discrete form of convolution, right? We're convolving the two densities. All right, well, we know what the densities are, so we just plug them in and then just do some algebra. So this is going to be the sum. M goes from 0 to n. The probability x1 equals m. That's going to be lambda 1 to the m, e to the minus lambda 1 over m factorial. The next one is going to be x2 is n minus m. So it's going to be lambda 2 to the n minus m, e to the negative lambda 2 over n minus m factorial. So I have a sum, m goes from 0 to n. I have m factorial and n minus m factorial. Who hears the screaming? Yeah, we want to put in n factorial. Because if we put in n factorial, then we're going to get a binomial coefficient. So again, it all comes down to trying to find a way to see the algebra as it's coming. So now we'll have n choose m, lambda 1 to the m, lambda 2 to the n minus m, and then it's e to the negative lambda 1 plus lambda 2. Oh, but what is this sum equal to? And we need a 1 over n factorial. So let me put the 1 over n factorial outside. So what is that sum equal to? Binomial. It's just lambda 1 plus lambda 2. So we get lambda 1 plus lambda 2 to the n, e to the minus lambda 1 plus lambda 2 over n factorial. And you can see why I can do this lecture without notes, right? It's really just follow your nose. It's just plug in. How do we do things? We do things by convolution. And then no, because this is the probability it takes on the value n, right? And so the proof is really just, it's always the same. And because we have an idea of what we're trying to prove, I know how to adjust things. Yeah. I want to get lambda 1 plus lambda 2. This is looking like the binomial theorem. So the binomial theorem is doing a lot of work today. All right, any questions? We've got on the order of 11 minutes, 10 minutes to show how the central limit theorem applies Stirling's formula. Okay, I think we can make it. So from the trailer earlier today, normal distribution, here's the density, and your sums of independent identically distributed converge to being normal. And there's lots of different ways we can do it, depending on how we want to average. So what we want to do now is we want to look at sums of Poisson random variables. So Poisson random variable with parameter lambda, it has density lambda to the n, e to the minus lambda over n factorial. And let's let x1 through xn be independent, identically distributed random variables. This is the central limit theorem with mean mu variance sigma squared. Then the sum converges to being normally distributed with mean n times mu and variance n sigma squared. So here, let's let x k be Poisson with parameter 1. So what is the expected value of xk? It's just 1. And what is the variance of xk? 1. But is that the variance or is it the standard deviation? Doesn't matter, right? This is why I always love working with something where it's normalized so that it's 1. So if you screw up and you use the standard deviation instead of the variance or vice versa, you're okay. Obviously, I feel a little cocky about finishing in 10 minutes if I'm making comments like this. Okay, so we can now apply the central limit theorem. So let's let x be x1 plus xn, and this is going to be Poisson. What's the parameter going to be for this Poisson? Each individual one is a Poisson with parameter 1. So the sum is going to be Poisson with parameter n. What is the expected value of x going to be? N, and the variance of x. Not n squared, just n. The variance of a sum of independent random variables is the sum of the variances. Each one has variance 1, so the variance is going to be just n. So this means x converges to a normal with mean n and variance n. Right? That's the central limit theorem. The central limit theorem, we haven't proven the central limit theorem. The central limit theorem says if you have a sum of independent, identically distributed, nice random variables, so as Poisson gets large, it's going to look more and more like a normal random variable. But this is the power of a stable distribution. And so this time at the end of class day, I will punch up some plots. So we know that X is converging to be normally distributed with mean n and variance n. But we also know that it's a Poisson random variable. What do you think the most interesting place to evaluate this Poisson random variable? What choice of integer? We know that this sum is converging to a normal centered at n with variance n. So what's the one place we'd like to calculate? The probability that X equals what? You can only give me one value. Well, 0, the probability that it equals 0 should be tending to 0. Because if it's becoming normally distributed, here's the mean n, the variance is going to be of size n. So this is going to be on the order of square roots of n. Oh, that is horrible. So what's the value you would like to calculate the probability of X? Not n plus, just n. Right at the middle. Right? Well, we know that that probability is just lambda to the n, e to the minus lambda over n factorial. Lambda is n. So we have n to the n, e to the minus n over n factorial. Oh, holy shit. Right? You want to talk about something made for Stirling? Where it's coming from? Okay. That's looking damn good. Right? So now we know that X is approximately a normal with mean n and variance n. So what is the probability that X is in, say, n minus a half to n plus a half? Why am I going to plus or minus a half? Well, the reason I'm going to plus or minus a half is, remember, the normal distribution is continuous. And so this is talking about finding the probability under the normal curve that's closest to the integer n. Right? And so that's where this is coming from. Okay. So now when you look at this, how would we find this out? Well, we would have to estimate the integral. So here's n plus 1/2, not going to scale. Here's n minus 1/2. And so we want the integral from n minus 1/2 to n plus 1/2 of 1 over square root of 2 pi n, because that's the, then you have e to the negative x minus the mean squared over 2n. Right? Well, when x equals n, what is the exponential? It's just e to the 0. It's just 1. As you move all the way to either n plus or minus 1/2, you get e to the negative 1/2 squared over 2n. So you get e to the negative 1 over 4n. So e to the negative 1 over 8n. When n is huge, e to the negative 1 over 8n is approximately what? Not 0. It's approximately e to the 0. It's approximately 1. There's really no change as we go from n to n plus 1/2. The change is negligible. So this is approximately the integral from n minus 1/2 to n plus 1/2 of 1 over square root of 2 pi n times 1 dx, which is just going to be 1 over square root of 2 pi n. But we know the probability that x equals n was n to the n e to the minus n over n factorial. So n to the n e to the minus n over n factorial is approximately 1 over square root of 2 pi n, which implies n factorial is approximately n to the n e to the minus n square root of 2 pi n. And this wasn't even 10 minutes. So this is what happens when they let a mathematician teach 341. This is not something I think that they would be celebrating on the stat side of the department. But it's good to see. When you see the central limit theorem, you think about the central limit theorem to estimate probabilities. Here is another application of the central limit theorem. If I can find a way to connect various objects, I can use the central limit theorem for many different things. Now, I want to end the day with a warning. I want to calculate the limit as x goes to 0 of the sine of x over x. So how would you calculate this? What would you use from calculus? You use L'Hopital. And you know you've made it when your name becomes a verb. You L'Hopital it. And what's the derivative of sine of x? And the derivative of x. And so this limit is 1. Okay. Cosine of 0 is 1. Okay. Careful. We need the derivative of sine of x is cosine of x, right? How do you find that? You need to calculate the limit as h goes to 0 of the sine of 0 plus h minus the sine of 0 over h, which is the same as the limit as h goes to 0 of the sine of h over h, or if you just swap letters, x goes to 0 of the sine of x over x. So this is the fundamental limit of trigonometry. All of differential trigonometry depends on this limit. Once you know that limit is 1, then everything follows. And it's 1 only if you use radians. The derivative of sine and cosine do not flip if you use degrees. It all comes down to this limit. You have to be careful. We'll end with one last one. The limit is n goes to infinity of the sine of x over n. So you say 0. Does it matter what x is? Yeah, what does the numerator live between? Anybody know why it's 6? All right, just another here you need to take care of with limits. All right, this is a good place to stop.